Yes, hi. Hi everyone. Good morning. Hmm. Yes, what did we study in the last session, guys? All right. All right. So let us discuss the or let us continue with the last session that we have. Let's continue from that. So this is your drive link. Yeah. So in the last session, we have seen the clustering approach, right? So the centroid is calculated by computing the mean of each and every column dimension that we have seen, right? Centroid is calculated by computing the mean of each and every column or dimension that you have, and then ordering them as we have ordered over here, right? So the height centroid is this, weight centroid is this, and age centroid is this. Now that you have understood the centroid, let us go to the steps of the algorithms. So let's go through this. Let's consider we have a set of 10 points, set of 10 points on a plane, and we are trying to group this into, let's say, two clusters, right? And let's see how Kmeans algorithm achieve this goal. Now, if you don't know what do you mean by Euclidean distance, you can try that out, but we already have seen that what is Euclidean or Euclidean distance, right? We have seen that. So let's say um, before moving ahead, let's think about the following problem. Let's say you have data of 10 students here, right? And you have their marks in biology and their marks in maths, right? And you want to divide them into two clusters so that you can see what kind of student are there in the class. So over here, your y-axis will show biology and x-axis will show math. X-axis will show math, y-axis will show biology. Right? Now imagine two clusters dividing this data. One is red, you have these two data points, or not, you have data points like this: 1, 2, 3, 4, 5, 6. Let's say here, 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 and here, right? We have these data points. Let's say, let's imagine you are trying to um, you're trying to put that into two clusters, let's say red and yellow. So how will you do? The very first thing is we'll find the centroid, right? Consider all the data points have some coordinates like x1 and y1. Yes or no? All the data points will be having some coordinates like x1, y1. So for this point, y coordinate we have. For this point, we have x coordinate. So likewise, we have all the x coordinate and y coordinate, right? Now let's see how do we achieve this thing now. So what we do is we start our process by choosing k initial centroids. K initial centroids. You start your process by selecting k initial centroids. So centroids can be anywhere. Randomly, you just put centroid. Let's say you want two clusters, right? So for an example, what you'll do is you will just kind of um, take two clusters and start choosing centroid anywhere randomly. Let's say this is my centroid and this is my centroid, right? Anywhere randomly. So start choosing k initial centroids. So we are we are good to go with the two clusters. We have opted for two clusters. So we'll select two centroids, right? Now we'll find distance of the data point. Suppose distance of this data point from this centroid, distance of this data point from this centroid. We'll find that, right? Right. Then we say that as the distance between this data point and yellow centroid is closer, so this particular data point is my yellow cluster data point. This data point is my, it is having, or it will be there in this cluster, which has the centroid, this one, yellow, right? So likewise, we'll find distance of all the data points. All the data points, this is closer, so yellow. This is also closer, let's say. So this is yellow, but this one is red. Yes or no? This is closer, let's say. So this is red. This one is red. This one obviously red. This one is red, right? This one is also red. And what about this other points? This one is yellow because this distance is minimum as compared to red distance. And this distance is also, let's say, yellow. Let's consider. We have not calculated the distance, but after calculating the distance, we concluded that these are the yellow data points and these are the red data points, right? So step one is assignment step. What do? Is we write down step one, the assignment step. We call it as assignment step. Then we have step number two, that is your that is your optimization step. Optimization. What is optimization? So suppose if you try to draw a cluster, so yellow cluster will look like this, right? And red cluster will look like this. Yes or no? But what we have discussed is centroid is the center of the cluster, right? What is the definition of centroid? What's your definition for centroid? It's the center of the cluster, right? Center of the clusters. So what do we do then? We try to shift the centroid position to the exact center of this cluster, of this body. So we'll be locating this centroid over here, locating this centroid over here. Then again, we'll find the distance, right? If the distance is minimum, let's say now uh, you have concluded that, let's say this is your centroid, right? And red centroid is over here, center of the body. Then you'll find distance. Let's say, for an example, you have concluded that this data point is closer to the red centroid rather than yellow. So then it will be part of red. So likewise, the thing will happen. Again, there will be a formation of cluster. Again, there will be formation of cluster. And again, you'll calculate center of the cluster, find the distance between the data point and cluster. Once this gets finalized, right? Once this gets finalized. So that's how your K-means clustering works, right? Its aim is to is a aim is to maximize the tightness or closeness of the cluster. That's why the optimization step is carried out. Its aim is to maximizes the tightness or closeness of cluster, right? And maximizes the distance between the clusters. Distance between the clusters, right? So the step is optimization step is your each time the clusters are made, the centroid is updated, right? And the updated centroid is the center of all the points which fall in the cluster associated with the centroid. And this process continues till the centroid no longer changes. That is the solution converges, right? This process continues till the centroid no longer changes. That is the solution converges. Is it clear now, everyone? So that's your step. That's how it works. You don't need to worry about this because anyway, this happens in the back end, right? So that's why the step happens. All right. So let us move towards the mm, let's discuss the another problem that is associated with K-means. So I'll just take out one presentation. Mm. See, it's an unsupervised machine learning algorithm. It is one of the simplest and most common clustering techniques. K in K-means clustering denotes the number of clusters to be formed, right? So suppose you have a data like this, and your what is expected from K-means is to categorize this data into different clusters and give us the output, right? So these are the steps that we have discussed. I assume you guys are already aware about this thing, like creating or defining a centroid to directly form the clusters, right? This is your data point. Now you will be having a question, how we find the best K value. How do you guys find the best K value for your data? Best K value. How do you find best K value? Yes, guys. So in KNN that we have discussed, in KNN that we have discussed, how do we use to find the best K value? What was the solution for that? Yes, everyone. KNN, how we used to find the best K value in KNN? Chalo, who will answer this?
We can take random numbers, sir.
No. Elbow curve we have seen, no? Elbow curve. Do you remember that? Yes or no, guys? KNN we have discussed, no? Or is it not discussed, KNN? Come on, guys. KNN is it not discussed for your batch? Okay, I think it's not discussed. It's not discussed, right, KNN? Yes, sir, I'm not getting. Is it discussed or not discussed? Just write down that in the chat. Discussed or not discussed. Random forest, identity, SVM. Okay, KNN is not done. All right, no problem. Uh, See, what happens is we'll be discussing this KNN also. But what happens is, what do you do is on y-axis, you calculate WCSS. I'll explain this, what is WCSS is all about. And on x-axis, what do you have? You have number of clusters. First, we select random number of clusters, right? We select random number of clusters, random K value. So K value is random initially. Then, uh, then what happens is we generally, but we are interested to, we'll get some accuracy over here. We'll get some accuracy for the model that we have fitted. But we are interested to find the best k value, right? What will be the best k value so that we can get the maximum accuracy. So what we do is we take, we find, suppose this is your centroid. These are the data points in that cluster, right? So WCSS means within cluster sum of squares. Within cluster sum of square, WCSS. So what do we do is we find the distance of each data point with respect to its centroid, right? And as the distance can be positive, can be negative, so we take square of the distance, right? So we take within cluster sum of squares. And on x-axis we have number of clusters. So let's say if the cluster value is 2, within cluster sum of square is, let's say, 100. Let's say 101 or 110. If your cluster value is, let's say 1 or 1, so your within cluster sum of square is very high. Means only one cluster is selected. Only one cluster is selected. The distance is very high, right? Distance of the data point from the cluster. It's very high. Means WCS is very high. So that is not good part of the cluster. What is the good, uh, like what is expected from the cluster is within cluster should be as minimum as possible. Within cluster sum of square, WCSS should be WCSS should be as minimum as possible. Why? Because see, suppose you have this data points 1, 2, 3, 1, 2, 3, and 1, 2, 3. You are taking only single cluster, let's say. You are taking only single cluster. So within cluster, sum of square of these data points will be very high. Yes or no? Yes or no? But instead of this, you take two clusters now. Even though ideally it should be three clusters, but let's say you take two clusters. So for this cluster, within cluster sum of square is very less, very good. Means all the clusters are tightly, all the data points are tightly attached or packed to the particular cluster. But what about this? For this, cluster centroid will be here, and the distance between all the data points with respect to its centroid is very high. So within cluster sum of square is high. So ideally, it should be three clusters. Three. 1, 2, 3. 1, 2, 3. 1, 2, 3. Right? Here, here, and here. So this is your centroid, right? And the distance between the centroid and the data point will be very less. Yes or no? So within cluster, sum of square should be as minimum as possible. Right? Should be as minimum as possible. Chalo. Is it clear now, everyone? So what do we do is, on x-axis we have number of clusters, on y-axis we have WCSS. For two cluster, it is, let's say, 110. For cluster value 3 is very less. Very less. And this is also less. But it should be, as a matter of fact, it should be, number of clusters should not be as high as possible. If you take 10, that is also allowed, no problem. Nothing will happen. But your model will overfit, right? Unnecessary, you are becoming your model, you are doing complex, right? Because number of clusters are high, so there will be high number of clusters, unnecessary, right? So what does this curve says? Elbow curve. First of all, why it is called as elbow is because It looks like your elbow of your hand, right? Basically, this is your elbow of hand, right? So wherever there is a bend, we generally take the minimum. We generally take the that as the best value of k. Wherever there is bend in this curve, that is elbow, that represents your what? Best k value. So this is your hand. Suppose where is your elbow? Here. So anywhere between these two data points, these 2 points, you can have number of clusters. Anywhere between these 2 points, right? Anywhere between these data points, you can have your clusters. Simple. But nothing will happen, to be honest. If you take k is equals to 1, you will get little less accuracy, not the best accuracy, but your model will be underfit. It will be very simple model. And if your k value is very high, let's say 10, your model will overfit. If your cluster value is very high, so your model will overfit. It will overfit. Cluster value, if it is very high, so it will overfit. Like unnecessary, you are making model complex, and your computational cost will be high, computational time will be high, processing time will be high, right? So it should be optimum. It should not be very high, not be very less, right? That's what the idea is. So basically, we are going to plot this WCSS curve and number of clusters curve. Just remember what is elbow curve. You should be able to say 5 points in the interview at least. 5 points in the sense like what is there in on y-axis, what is there on your x-axis, then why it is called as elbow curve, how do we find best k value, how do you find best k value, right? That's what we have, right? More than sufficient. So the idea to find the best k value is by using elbow curve. So that is solved. One problem is solved. But we have another problem. What is that? That is a random initialization trap. That is a random initialization trap. Random initialization trap. Right? So let's see about let's have a discussion on that. So what is random initialization trap? So suppose you are fitting any random first. What is the first step? Select random centroids. Random number of clusters. Random k clusters, right? So suppose we have 19 students over here, right? All of you guys will not be going with the same number of clusters. Yes or no? If I say random number of clusters, what will do? Suppose you will select 3 clusters. Those three would be like this, right? Suppose some of you guys will feel that there should be 4 clusters like this. 1, 2, 3, 4, right? Suppose you guys will feel that this is one cluster, these are the 2 other clusters, right? Or only 2 clusters are needed, right? So it can be n number of possible conditions, yes or no? So your model, if you give, you just have to provide k is equals to 2 or 3. Let's say you have taken k is equals to 3, right? You have taken to initially to fit the model, you have taken K is equals to 3. K is equals to 3, right? So if K is equals to 3, if K is equals to 3, so your first model is doing like this, 1, 2, 3, right? Suppose if somebody other guy has selected K is equals to 3, for that K is equals to 3 is equals to this 1, 2, and 3, right? So it can be anything like 1, 2, and 3, like that also possible, right? So you don't have any control over the combination of the fixed combination of the centroid or of the cluster, right? So that is known as random initialization trap. Randomly initializes the centroid. It's so basic, your model will not understand uh, how to provide the cluster or how to just adjust the clusters according to that particular data. So what is random initialization trap? It's a problem that occurs in Kmeans algorithm. In random initialization trap, when the centroids of the clusters to be generated are explicitly defined by the user, then inconsistency may be created, and this may sometimes lead to generating wrong clusters in the dataset. So random initialization trap may sometimes prevent us from developing the correct clusters, right? May sometimes prevent us from developing the perfect clusters, or what we can say, developing the correct cluster. So suppose ideally correct clusters are like that, right? But due to random initialization trap, your model is stuck in the initialization trap and it is not able to achieve that ideal correct clusters combination, right? So suppose you have a data set with the following points shown in the picture, and you want to generate three clusters in this data set according to their attributes by performing. So they have explained this thing, same thing only, like three clusters can be like this, or it can be like this, or it can be like this, right? So in order to avoid this random initialization trap, we use K-means plus plus. So what is that? It's nothing special. It's an improvised version of K-means. It avoids random initialization trap. So these are the limitations of K-means. K-means are sensitive to outliers. You have to define uh, in advance the number of clusters, which may not align with the actual data distribution. And K-means perform best with round and evenly sized clusters, making it unsuitable for irregularly shaped or evenly distributed cluster, right? So what do you do is to avoid that, we just write down init is equals to K-means. Or instead of that, if you just go to official documentation of K-means, if you just go to official documentation of K-means, and if you just go to sklearn official documentation, so you just write down while fitting a model, we have a parameter init is equals to K-means, right? Init is equals to K-means plus plus. So while fitting a model, while creating an object, just like in decision tree, we used to write n underscore neighbors, right? Maximum underscore split, right? We used to write down that. Do you guys remember this? Right? Criteria on we used to pass, or splitter, or max depth, or minimum sample split, or minimum sample leaf, or anything, minimum weight fraction, or maximum fixed feature, or random, so anything we can pass, right? So these are known as parameters in decision trees. In K-means as well, we have to pass init is equals to K-means plus plus, and which is usually deals with the uh, will solve the problem of random initialization trap. And what it does is it selects initial cluster centroids using sampling based on an empirical probability distribution of the points, contribution to the overall inertia. This technique speeds up the conversions, and it is implemented is greedy K-means plus plus. It differs from vanilla K-means plus plus by making several trials at each sampling step and choosing the best centroid among them. So directly it will choose best centroid. It will not be having any combination. If you just write down K-means plus plus, right? Directly you'll be having some combinations like that. So best combination. So the problem of random initialization trap is also solved by using Kmeans plus plus, right? So that's what we have for this entire Kmeans plus plus. So what I'll do is now let's create new folder. I'll just add 12th Jan Kmeans, right? And I'm going to share this presentation and I'll add a data set. Then we'll be having a short break of 5 to 10 minutes. And then we'll be actually going with the model building part for Kmeans, right? So the presentation that you guys will require is this one. And the data that we have is this. This is your data, right? Let's create new collab notebook. Yeah, I'll just put this as K-means on mall customer. And we'll be having a break now. It's 9:49. Let's have break till 10, right? And after the break, we are going to fit the model. So we are going to use WCSS. We are going to use K-means plus plus, basically the elbow curve here, right? Then we are going to visualize the clusters after the break. All right, so let's have a break. Yes. All right. So we will be actually loading our data. Let us load the data. This is our data, right? And then let us start working on this mall customers case study. All right. So let us import necessary libraries first. We are going to import pandas as PD. Oh, sorry. Importing the necessary libraries. Import pandas as PD. Import numpy as np, right? And we will require package. We visualize the data, so matplotlib is sufficient. Importing matplotlib.pyplot as plt, right? And then from sklearn.cluster, I'm going to import Kmeans. So I'm going to write on df is equals to pd dot read underscore csv. And I'm going to copy this path and I'm going to paste it over here. Then df dot head, right? So the problem statement is the problem statement here is we have customers data from mall and mall wants to make strategy for this customer so that they can spend good amount of money. And imagine imagine you are working as a data scientist. You have to create a strategy for this type of problem set, right? So I'm going to write on df.info. Then I'm going to write down x is equals to df of double square bracket. I'll take annual income k dollar. So basically in x, we are only interested in these two variables because age, gender, customer ID are uh, do not they do not have any satisfactory, or they do not have any significance, right? So we'll take spending score and 1 to 100 column name. Basically we are taking a subset of that of this data, and let's try to analyze the second record in this. So x iloc second, that is 15 comma 81. So it is good. So directly we are interested to create an elbow curve now. So let us put heading as elbow curve to find the optimal number of clusters. Right. So WCSS is equals to a blank list for k in range of 1 to 11. Small k means what is this? I'm adding this in text cell, right? We'll create a blank list. WCSS is equals to blank list for k in range of what? Let's select 10 clusters, right? So we are iterating through We are iterating or iterating through 10 clusters here, right? So let's not focus on this. Let's put it up here. Yeah. So small Kmeans is equals to the package for Kmeans. What was that? This is your package, right? If you just go to Kmeans official documentation, you'll be able to get that package. Nothing difficult over here, right? So how to import Kmeans package? You can see over here. You will just have a look at this from Kmeans. It's from sklearn.cluster import Kmeans. And how do you create a variable? You can create like this, or you can create uh, like this as well. So Kmeans equals to package capital K capital M means. In that, number of clusters are basically, see, what are the different variables that you can pass in this Kmeans? You can pass number of clusters, you can pass init, you can pass string, max iteration, right? Or you can take help of these parameters. What are the different parameters that we have? We have these parameters. So you can pass anything. So if you are passing number of clusters, the ideally the value should be integer, and you're taking a k value, which is this in the range of 1 to 11. Then you have in it is equals to k means plus plus comma random state is equals to 3. Random state is equals to 3. And then small k means dot fit it on x, wcss dot append small k means dot inertia underscore, right? And then we are going to plot this. So plt dot plot in the range of 1 to 11, in the range of 1 to 11, comma wcss, right? Then plt dot title. My title for the graph is the elbow method. The elbow method. Then plt dot x label number of clusters. Plt dot y label wcss and plt dot show. Plt dot show. So WCSS is this for k in range, this one, fitting this. Then WCSS is a blank list that we have created. We're appending k means dot inertia in that. And then we are plotting the line plot for, on x-axis we have 1 to 11, that is your k value. And WCSS is there on your y-axis, right? Then plt dot title, by title of the curve is elbow method. X label is number of clusters, Y label is WCSS, right? So I'm going to build the model. I'm going to write down model building part. So small k means is equals to capital K means n underscore clusters is equals to 5. Init is equals to k means plus plus comma random underscore state is equals to 3. Then k means dot fit it on x. And capital clusters is equals to k means dot predict on x. So basically, these are nothing but your model building. You're creating an object, you're fitting in, and then you're predicting. So the stages of your model building, step number 1 is object creation, right? What was your step number 2? That was model fitting. What is your step number 3? Is your model prediction. right? And then you are going to write down clusters. So these are your clusters. These are your clusters. Now I'm going to visualize these clusters. So I'm going to write down visualizing the clusters. So plt dot figure size is equals to 8 comma 8. Then plt dot scatter x dot iloc of clusters is equals to 0 comma 0 comma x dot iloc clusters is equals to 0 comma 1 comma size is equals to 100 comma color is equals to red comma label is equals to cluster 1. Then plt dot scatter. I'll explain this once I write down this. I'll explain each and every point. Don't worry. plt dot scatter x dot iloc clusters. Okay. So we can copy this entire line and we can paste it over here. Right? 30 is done. It's happening or it should be like this. Okay. Cluster 4. And last is 5, right? Because yeah, I have not asked this question. What should be the ideal value of cluster, guys, from this elbow curve? What do you think? What should be your ideal value of K or the best value of K? What is your best K value? Anywhere between 2 and 4, right? But if you just observe, the minimum is the bend is over here, right? Here also we have bend, but minimum bend is here. So let's take 5. That is your minimum value, right? And anyway, we are taking we have 5 is not that high a number, right? It's not that high. 3 is also good, not 2 exactly. 2 is here, right? So answer is not 2, anywhere between 2 and 4. That should not be the answer. Answer should be anywhere between 3 and 5. Because for 2 we don't have bend, right? So let us take 5. Number of clusters equals to 5. So that's why we have taken 5 over here, right? And why we have added Kmeans plus plus over there. Why is it done? Why it is there, guys? Kmeans plus plus. Why we have added this Kmeans plus plus? Yes, guys, why Kmeans plus plus? Make sure random initialization trap is not there. Excellent. Only one student has answered this, right? So we are visualizing these clusters now. Plt dot scatter plot between K means cluster 5 is there, right? Then plt dot scatter between K means cluster centroids, right? Plt dot title for the graph is cluster of customers, annual income, and plt dot legend plt dot show. Sure. Let us do this. So what is happening is What is happening is we have clusters of customers. Yes or no? We have this clusters of customers. So in X, what do we have? What was there in X? We have two columns, that is annual income and spending score, right? So I'll just write down over here before just doing this. What is there in X? If you just don't remember, in X, we have annual income and spending score. So X dot ILOC cluster 0 of 0, right? X dot ILOC. If you write down X dot ILOC and cluster 0, if you just write down this, you will get the entire data, right? But what you're interested to do is in this line itself, you're interested to find zeroth record, right? Zeroth record means what? Your annual income column. So if I write down cluster is equals to 0 comma 0, not 0 actually, 1 comma 0, or 0 comma 0 is also fine. So if I write 0 comma 0, what I'll get is I'm getting the data points which are from annual income column, but which are of cluster number 0. Data points from cluster 0 part from which column? From annual income column. Yes or no? Then I am having another thing. Let's take another thing. Cluster dot x dot ILOC. If I just write down 0 comma 1. So cluster 0, but part of which column? Spending score. So the data points from cluster 0, 0, part of spending score column, right? So likewise, these are the data points from cluster 0 from first column and data points from cluster 0 from second column. Cluster 1 from first column, cluster 1 from second column, cluster 2 from first column, cluster 2 from second column. So basically what we are taking is in the line number 2 itself, we are taking cluster number 0 data points for annual income as well as spending score, renaming that data points as or coloring that data point as red, labeling them as cluster number 1. So cluster 0 is having red and the name of that is cluster 1. So this is your cluster 1, but that is your data points from both the columns, which is a part of cluster number 0, right? Similarly, on the line number 3, we have data point from cluster number 0 from cluster number 1 from both the columns, coloring them as blue, renaming them as cluster number 2, right? Cluster 2 data points from all the columns, that both the columns from cluster 2, color is green, cluster is 3, right? Is it clear now, everyone? Is this thing clear? Yes, guys. Do you have any questions in this? Anybody have any questions in this? All right. So let's try this. You try this out, guys. I'll give you 5 minutes of time. Try this out. And here, what will be our strategy? We already have discussed that. We'll target which color clusters, guys? Just think on this. These are your annual income and spending score. We are going to target which color clusters? Yes, guys, which cluster we should target? We should target green. Why green? We should target green. Why, guys? Blue. Blue is the correct answer. Yes. Red. Red is bad. We already have discussed this statement, guys. See, we should target those customer. We should target those customer whose annual income is high, but spending score is less. Spending score is less. Whose annual income is high, but the spending score is less. Right? It means that they have potential to, go and shop, but they are not doing this, but they have potential. Anyway, we will not target green because they are having high annual income, but the spending score is high, right? At max, they will not end up spending more in your shop. In this thing, if you just target this, uh, which color? Magenta color, this one. If you just target this customers, they are having less annual income. So their spending score is less, right? They don't have any potential. So we'll be targeting which clusters? Only cluster number blue. That is your, this cluster number one. So cluster number one for all the data points. Cluster number one for all the columns out there. Cluster number one for all the columns out there, right? This is your data. Is it clear, everyone? Is this thing clear now? All right, then I think we are good to go for the next part. That is your hierarchical clustering, right? All right, perfect. So let us uh, let's work on one more model building part. Let me check. Do we have other data set or not? We have a look there. We are interested to work for Kmeans, right? All right. Just give me a minute. I'll just download the data and upload it on your drive. Data set. So the data that we have is online retail. This one. Where is your drive? Let us work on another project. So this is Kmeans, right? Here I'm just going to upload that particular data. I'll just open collab, create, share. Perfect. Okay. So we will be using Kmeans, working on Kmeans. Let us upload the data. This one, right? And let's start working on Kmeans clustering. So overview is online retail is a transactional data set which contains all the transactions, which contains all the transactions occurring between 1st of December 2020 and 9th of December 2020. So 2011, 2010 for a UK based and registered non-store online retail data. And the company mainly sells unique all occasion gift, right? Company what it does is it sells unique all occasion gifts, and many customers of the company are wholesalers. So the steps are broadly we need to read and understand data. Second is we have to clean the data. Third is we have to prepare the data for modeling. Fourth is modeling. And fifth is final analysis and record. All right. So let us read the data first. Read and visualize the data. We'll import numpy as np. We'll import pandas as pd. Excuse me. We are going to import matplotlib dot pyplot as plt, importing cbon, importing date time as dt. We are going to do some data pre-processing as well. So from sklearn, standards killer, Kmeans. Seal out score, I'll explain. PCA we already have not done till now, so we'll not be doing this. And hierarchical clustering is something which we have not discussed, so we'll not be discussing this as of now. So let us read the data. So my retail underscore df is equals to pd dot read underscore. The file is having CSV extension, right? CSV. So pd dot read underscore CSV online underscore retail dot CSV, comma SCP is equals to this one, right? Comma encoding is equals to ISO 88591, comma header is equals to 0, and retail underscore df dot a open and close bracket. Online retail dot CSV is not there. Okay, I need to copy path here, right? Then we are going to write down basics of the data frame df. So retail underscore df dot info. Then we are interested to clean the data because we have missing values. If you see, we have missing values in this data. 1454 customer ID has one 1,35,000 missing values, right? So first of all, we will be finding, we'll round off 100 into retail df dot is null dot sum divided by length of retail underscore df dot index, comma 2, right? I'll just run this. Then we'll drop all rows having missing values. So retail underscore df is equals to retail underscore df dot drop null values, and then retail underscore df dot shape. So we are dropping all the missing values in our data, and then we are checking our uh, data set shape. And then if we check the null values over here, so we are having this much null values, 0. It's 0 now, right? Now we are good to go with what? With next step. Now in this data, if you see retail underscore df dot head, this data, you just see this, you will be if here we have quantity and unit price, right? Unit price, right? So if I just multiply this quantity into unit price, I'll be getting total amount, yes or no? Like this particular product, white hanging heart light holder or white metal lantern, 6 into 3.39. I'll be getting the total amount, right? So I'm going to create a new column called as, let's call that amount, that let's call that column as amount. And then I'm going to write down retail underscore df of what? Of amount is equals to retail underscore df of what? Quantity into retail underscore df of unit price, right? And then I'm going to write down retail underscore df dot head, open and close bracket, right? Dot head. Then I'm going to prepare the data for modeling. So let's call it as prepare data for modeling. So I'll be write on R, that is recency wise. R is for recency. The metric is basically for our retail store. F is frequency. And M is monetary. So recency is number of days since last purchase. Frequency is number of transactions. Total amount of transactions, that is revenue contributed, right? Now, aim is monetary over here. So I'm going to write on group underscore df is equals to retail underscore df dot group by customer ID, then amount column, and I'm going to find sum. Then group underscore df is equals to group underscore df reset dot index, and then group underscore df dot head object has function object has no attribute head. Okay. Why we only have one? We are interested to the reset index is not done, no? Because to group. Yeah, why we are resetting the index, guys? Because customer ID is over here, right? That is considered as index, but I don't want that as to be part of index. So I'm just resetting that index. If I do this, I'll be getting, and if I just check what is there in grouped df, I'll be getting the output, that is customer ID and amount, right? Perfect. Similarly, we'll do this for frequency. How do you calculate frequency? Is frequency is equals to retail underscore df dot group by customer ID and invoice number and its count, and then we'll again set the reset index for this. So customer ID and invoice number. So basically count. So this customer is 2 times. This customer ID is 182 times. So what we'll do is we'll just change columns name, column names to customer ID, comma, frequency, right? All right. So that's what we have. Then we are going to merge these two data frames. Merge the two DFs. We'll write on grouped underscore DF is equals to PD dot merge. What we are going to do? We are going to merge this two data frame, that is frequency data frame and your earlier, what was that? Grouped DF. Let us merge these two data frame. In order to merge this two data frame, you need to write down PD dot merged grouped DF and PD dot merge group DF and frequency, right? So grouped GROU grouped underscore DF from the frequency. On which column? So on customer ID column. How? How is equals to inner join. And then grouped underscore df dot head open and close bracket. Right. So this is how we have done the merging. And then in our retail df original data frame, which we had, open and close bracket, we'll find recency, that is will convert it to date time. Convert to date time. We'll write on retail underscore df. We have invoice date, right? The data frame. So basically, the column for or the data type of that column is not date time. Retail underscore df dot info. Date type, data type. Can you see this? Invoice date. It is an object. It has to be date, right? So we'll convert that into date time. How do you do that? You write down invoice date and we write down pd dot to date time retail df of invoice date. Simple. And the format that I want is, it should not be just a minute, time date. Okay, the format, this is what I was talking about. I want this format. It does not match, right? This is m, month, date, year, hour, then minute. We have it has to be date, month, year, hour, and minute. So let us modify that, right? We'll write in format is equals to percentage d, percentage m, percentage y, space, percentage h to percentage m, right? And then we'll write on retail underscore df dot head, open and close bracket, right? Then we are going to compute the maximum date. Maximum date is equals to maximum of retail underscore df of invoice date of invoice date and maximum underscore date, right? Then I'm going to compute the difference. I'm going to compute the difference, that is retail underscore df of difference is equals to max underscore date minus retail underscore df of invoice date. Then retail underscore df dot open and close bracket head. Right? That's what we have. Then recency wise, last underscore purchase is equals to retail underscore df dot group by based on customer ID column and diff. We are finding minimum of that. Then last purchase equals to last purchase dot reset underscore index, and we are finding head of that, right? So that's what we have. Then, so this is last purchase, like customer number 12343. Last purchase, it since 325 days and this much time he has not purchased, or that particular customer has not purchased the product. Similarly for this, last purchase was 1 days before, right? 1 days ago. So that's what we have calculated, recency. Then after doing recency, we have merge. We have merge. What is that merge? Grouped underscore df equals to pd dot merge grouped underscore df from a last underscore purchase on which column? On customer underscore id column. How is equals to inner group df dot columns is equals to column name that I'm going to give. Basically, for this data group df, we are sorry, this is group spelling is wrong. Group df and customer ID is not customer underscore ID, it is customer ID like that. Okay, so what we are doing is we are actually uh, grouping our data, grouping or merging this two data, group underscore df and last purchase on customer ID common column, doing the inner join. But column names are customer ID, amount, frequency, and difference. Instead of difference, I want recency. So I'll just rename the column, right? I'm going to rename this column. So column name are this. And then again, you can check the head of the data. Uh, Length mismatch, it should have 5. Okay. Do we have 5 columns? Just a minute. If I just restart and run all this, we have 1, 2, 3, 4, 5. Difference 6 and difference 5. What is this? Same, because I have run this twice. Yeah. All right. All right. I should not run this twice. Again, I'll do restart and run all. Yeah, so we have 4 columns now. Perfect. Now, after doing this, we are just interested to change the column name. So grouped underscore df dot columns is equals to customer ID, comma, amount, comma, frequency, comma, recency. And then I'm going to write on grouped underscore df dot head, open and close bracket. Right? Grouped spelling is wrong. Okay. Now I want to find number of days only. Number of days only. So grouped underscore df recency is equals to grouped underscore df recency column dot dt dot days, and then group underscore df dot head, open and close bracket. Yeah. Then I am interested to do the outlier treatment. So I'll be writing down outlier treatment. Outlier treatment. So I'll write on plt.boxplot. Plt.boxplot. Grouped underscore df for which recency column. Outlier treatment for recency. Recency. So for recency column, do we have outliers? Yes, we have outliers, right? So there are two types, two methods to remove outliers. Two types of outliers. One is statistical outlier. Statistical outlier. Another one is domain specific. So let us try to remove the outliers. Removing statistical outlier. Basically, that is something which we have seen uh, beyond upper whisker and beyond lower whisker region, right? So how do you use to remove outliers, right? What we'll do is domain specific are something. Perfect. Okay. Let's define Q1 and Q3. What is Q1? First 25% of the data. Let's write down that. Let us write down Q1 is equals to, what is that? Grouped underscore df. Recency quantile of 0.25. Q3 is group underscore df quantile 0.75. Your IQR is this, right? IQR is this. IQR is this. Then what we can do is we are going to remove the outliers, right? So how do you remove outliers? We are going to select only those values. We are going to select only those values which falls in this region, right? So upper whisker and lower whisker, between lower whisker and upper whisker, we are going to select values. So my grouped underscore df, I'm going to select only that particular value, which should be less than lower whisker and which will be greater than a lower whisker and less than upper whisker, right? So let's write down that grouped underscore df. Select only those values in what? In which data frame? Grouped underscore df data frame. Which values you want? Grouped underscore df dot recency. Recency column, for recency column, it should be greater than which part? Q1 plus, sorry, not plus, minus 1.5 terms of IQR, right? It should be greater than that, obviously, right? Q1 minus 1.5 terms of IQR. This is Q1. This is Q3. Do you guys remember this thing, box plot, guys? If you are comfortable with this, then only you'll understand. This is Q3, this is Q1, this is lower risk region, this is upper risk region. So upper risk region is Q3 plus 1.5 times of IQR. Low risk region is Q1 minus 1.5 times of IQR. Q1 minus 1.5 times of IQR. So you're selecting which part, which region. These are known as outliers, right? This one, this one, this one, this one, this one. So you're selecting only this part, this. Why? Because this uh, this region will not be having outliers, right? We already have studied that. So it should be greater than upper low risk region, that is greater than Q1 minus 1.5 times of IQ, because this is right hand side, and Q3 minus 1.5 times of IQ less than or equals to, right? So ideally it should be greater than or equals to, that is fine. And so and grouped underscore df dot recency, it should be less than or equals to Q3 plus 1.5 times of IQ, right? So that's what we have for this. Now, is it clear what this line number 7? Do you have any questions in this? If you have any questions, we can discuss. Yes, everyone. Do you guys have any questions in line number 7? Anybody has any questions in line number 7, guys? If we remove outliers, all the outliers, some important data also removed, right? Happens, but best is to directly remove the outliers, because it is not anyway, it is not going to lead towards the, or it is not going to be important for your dataset or for your analysis. Let's say you are interested to do the analysis of bowlers, right? Bowlers. Let's say bowler and their wickets, something like that, right? And by mistake, you have data points of, let's say, some batsmen like Sachin, Dhoni, then Virat, right? You have these data points in your data, and um, so obviously they will lie over here. Sachin is having very less wickets as compared to uh, anyone who is a full-time bowler. Let's say Zahir Khan, right? Or let's take Kapil Dev, right? So this will be outliers. Virat and Dhoni will be having very, very less wickets, right? So your point of saying is, if we remove this, there will be chance of removing important information. It's not like that, right? This is not important for us. That's why we are calling it as outliers, right? It is not helping us out to do any analysis. So it's anyway, it's fine directly to remove the outliers. Best way. right? So that's what we have done outlier treatment for your recency column, right? Outlier treatment for recency column. Then we will do outlier treatment for frequency and outlier treatment for amount column as well, because we have selected three data, right? Three columns basically: amount, frequency, and recency. So this box plot was for recency. Same thing we can have for amount, yes or no? And we can conclude that amount also has outliers. My amount column will also have outliers. Yes, we have outliers. Similarly, my frequency column will also have outliers, right? My frequency column will also have outliers. My frequency column will also have outliers, right? You can see that over here. So let us remove one by one. We have done it for recency. Let's remove it for amount and frequency. So wherever you have says cannot perform RAND with data type Boolean. Recency, is it Boolean? Just a moment. Group underscore DS. Round bracket. Should not be round bracket over here, first of all. And round bracket. Close here. Yeah. So let us do this same thing for these two columns, no? Amount and which one? Frequency. So let's do it for frequency over here. So I'll just take this, copy, we'll paste it over here, we'll paste it over here, we'll paste it over here. All right. Let's do it for frequency. Spelling is wrong. Frequency. In our data frame, what is your frequency column? I mean, what is the spelling? It is FRUQUN. Okay. So FREQUE. Right. So you copy this, you'll paste it over here, and we'll paste it over here. Let's do that. It is done. Let's now do it for amount column. Amount, right? Let's copy this. Let us paste it over here. Let us paste it over here. Then we'll do rescaling. Rescaling. So RFM underscore DF is equals to grouped underscore DF. There is requirement, right? Scaling requirement is there. Why? Because this three or basically this what we can say, these three columns are not in a single range, right? Amount, frequency, and recency. Are they in single range? Obviously not. So let's do that. So let's create an object for scalar. We are using standard scalar. So instantiating the object scalar is equals to standard scalar, open and close bracket. Then we are going to do fit transform, fit underscore transform, rfm underscore df underscore scaled, rfm underscore df underscore scaled is equals to scalar dot fit underscore transform, right? And then we will be actually doing rfm underscore df underscore scaled is equals to pd dot data frame rfm underscore df underscore scaled and this. So it is scaled now. Perfect. Right. Now it's time to go for modeling part. So whatever we have seen till now, we'll be actually doing it over here. So only 4 steps are remaining for model building part. So I'll be actually creating a modeling over here. We'll write down Kmeans with some arbitrary K value. Small Kmeans is equals to capital Kmeans in underscore cluster is equals to 4. Maximum iteration is equals to 50. Kmeans dot fit on rfm underscore df underscore scaled. Fit spelling is wrong. Then elbow curve, we can do elbow curve. Elbow curve, how we used to find? How we used to do? We used to write down WCSS is equals to a blank list. Uh, for K in range, so I can literally take this thing and try to create the elbow curve. So it's allowed, copy and paste is allowed. You can directly do that, right? This one. Let's do it over here. So K means, yeah, right. Done. X is not defined. Okay, we are fitting it. We are fitting K means on this. No. On this RFM underscore DF underscore scaled. It's not defined. RFM. Yeah. Now this is your WCSS, and you can find that from this WCSS, we get an idea about what? About your K value. What is your best K value for this case? It is 3, right? 3 or 4 is also good. 3 is also good. Right? Is it clear now? This one, how you can do this? Now we are left with hierarchical clustering that will do it in the in this after some time after having a short break, and that will summarize this summarize will that will conclude your entire unsupervised machine learning, right? So only thing which we will left with is PCA in unsupervised, and KNN is also remaining for you guys, so we can also do that in the next session. So unsupervised, we have seen K-means in today's session. What is left with us is one concept of Silhouette score that will discuss after some time. And we are going to start with another unsupervised machine learning model, which is your hierarchical clustering. Again, very important or very interesting unsupervised machine learning algorithm. We'll see this thing after break. Now, if you have any questions, you can ask. Otherwise, we'll just have a break for 10 minutes again. Yes, guys, do you have any questions? Basically, what is silhouette score? It's one parameter that we use to check how the quality of clustering, and it's an evaluation parameter. So from that silhouette score, you get an idea about the clustering. Uh, if you just select two clusters, what is the silhouette score? If you select k is equals to k is equals to 3, that is cluster is equals to 3. What is the silhouette score? So it should be as minimum as possible. It should be minimum. We'll see that its significance and everything we'll see after the break. Silhouette score, right? All right. Let's have a break now. It's 11:20. Let's have a break till 11:30. And after the break, we'll be discussing the next part, right? Just don't go anywhere, uh, because we are going to see silhouette score and hierarchical clustering after the break. Yes. All right. So let us discuss the hierarchical clustering now. See, this is also another type of clustering, which is which use dendrogram. Basically, it's a tree-like diagram, right? Everyone knows what is the dendrogram. That shows how data points are connected and grouped, and it is where your machine learning meets the art of clustering, right? So, what is hierarchical clustering? First question. What is hierarchical clustering? What is that? It's an unsupervised machine learning technique used for grouping of similar objects into clusters, and it creates a hierarchy of clusters by it creates a hierarchy of clusters, hierarchy of clusters by merging them based on similarity measures, right? It uses bottom up or top down approach to just construct a hierarchical data clustering schema, right? So clustering hierarchical groups, similar objects, clustering hierarchical groups the similar objects into a dendrogram, and it merges similar clusters iteratively, starting with each data point as the separate clusters. So what happens is, in Kmeans, what we do is we uh, create separate clusters, right? But one cluster can have different data points, matlab multiple data points, right? One cluster can have multiple data points. But here we start with this point that every single cluster has only single data points, or basically, uh, it groups us data points in such a way that a cluster or data point has separate cluster. So this data point has separate cluster, this data point has separate cluster, this has separate, and this has separate clusters, right? So let's say we assign, these are the data points, we assign each of these data points to a separate cluster. Now, based on this similarity of these clusters, we combine the most similar data points like that, right? And we repeat this process until only a single cluster is left. So starting from different clusters for each data points and ending with only single cluster for all the data point. Only single cluster for all the data points. So we are essentially building a hierarchy of clusters. That's why this algorithm is called as hierarchical clustering, right? Now what I'll do is uh, we'll be actually taking one data set and we'll try to understand how it works in the backend. So there are basically two types of hierarchical clustering. One is your one is your agglomerative hierarchical clustering. Another is your uh, divisive, right? And this is what I'm talking about. So what we have to do is we have to decide. This is all about Kmeans. Yeah. Let's say we have these data points and we want to cluster them into groups. So we start with the single cluster, single group, single data point, single cluster. Then we can assign each of these data points to separate clusters, each of these data point to a separate cluster. Then now based on the similarity of these clusters, we can combine the most similar clusters together and repeat this process until only single cluster is left. Repeat this process until only single cluster is left. Now we are essentially building a hierarchy of clusters. We are essentially building a hierarchy of clusters. And that's why this algorithm is called as hierarchical clustering, because we are building hierarchy, right? Now there are two types of clustering as I discussed, agglomerative and divisive. Let us understand each one by one. Agglomerative is something which we have seen just now. Like we have four data points, four clusters will be assigned. And then at each iteration, we merge the closest pair to the cluster. Let's say this is your closest pair. These two are closest pair. So we are merging this in one cluster. So this is one cluster, this is one data point. I mean, these two data points are one data points, combining them to one. And this is again one data point. Then these two data points are closer, so green cluster, combining them. Now, these three data points will be having one cluster or one data point combined, and this will be having another. So only two clusters, so only two data points, so one cluster. So likewise, it does agglomeration. If you guys are aware about agglomeration, you will understand this, right? So, so yes, Gopi, fine. You may leave, no problem. Just go through the recording. If you have any other task, you may leave, no problem. So that's how it works. Then we are merging or adding the clusters at each step, right? Hence, this type of clustering is known as additive clustering or agglomerative clustering. Similarly, we have divisive as well. It works in exactly opposite way. So it does not matter if you have 10 or 100 or 1000 data points. All these data points will belong to the same clusters in divisive hierarchical clustering. So it will start from single cluster, then like that, then like that. So it will end up to single cluster, single data point, like that. So at each iteration, we split the farthest data point in the cluster and repeat this process until each cluster only contains a single point and it is done, right? So agglomerative clustering is widely used in the industry. Agglomerative clustering is widely used in the industry. Divisive is something is which we generally not use. So just remember only one thing, that we use agglomerative, and this is how it works, right? So now again, here very interesting example, very interesting example. See, in hierarchical clustering, we merge the most similar points and clusters in a hierarchical clustering. We know this. Now the question is, how do we decide which points are similar, which are not, right? So least difference is the answer, because this is distance based algorithm. We find distance between two data points, right? In hierarchical clustering, we have a concept called proximity matrix. We have a concept called proximity matrix. And this stores the distance between each point. This stores distance between each point. Let us take an example to understand this matrix as well as the steps to perform hierarchical clustering. Let us take an example to understand this matrix as well as the steps to perform hierarchical clustering. So let's understand this. Teacher wants to divide her students into different groups based on the marks. So we have 5 students, 1, 2, 3, 4, 5, and their respective marks, right? So we plot this, right? What we'll do is we plot this on X and Y axis. Marks is there on Y axis. Student ID will be there on X axis. We'll be finding distance. So 35, 28, 20, 10, 7, like that, right? And student ID will be 1, 2, 3, 4, 5. So we'll create a proximity matrix. First of all, we'll create a proximity matrix which tells us the distance between each of these points. Since we are calculating the distance of each point from each of the other points, we'll get a square matrix of shape n cross n. We'll get a square matrix of cross n cross n. So for an example, we have 5 data points, so 5 by 5 proximity matrix will be there. And this one, the distance between data point 1 and 1. What is that? It will be 0, obviously, because distance between the two same data points. Let's say distance between 1 with respect to 1. It's 0, right? Then distance. Okay, let me take this figure over here so that you'll understand it properly. All right. So now what we are doing is distance between 1 and 2. 1 and 2. It is 10 minus 7, right? So distance is 3. Again, distance between 1 and 3. 1 and 3 is 10 minus 28. This is 18. Then distance between 1 and 4. 1 and 4 is 10 and 20. That is 10. And distance between 1 and 5. That is 10 and 35. That is 25. Right? Similarly, all the distances are calculated. All the distances are calculated. Then we'll write down steps to perform hierarchical clustering. First, we'll assign all the points to an individual clusters. Different colors here represents different clusters. We can see that we have 5 different clusters for the 5 data points in our data. 5 different clusters for 5 data points in the data. Then what do we do is we'll look at the smallest distance in the proximity matrix. We'll look at the smallest distance in the proximity matrix and merge the points with the smallest distance. In this entire proximity matrix, what is the smallest distance? 0, don't say 0 because anyway 1 and 1, this 0 means the distance between the two same data points. 1 and 1, 2 and 2, 3 and 3. So they'll be obviously gonna be 0, right? They'll obviously going to be 0. But apart from 0, what is your minimum distance? What's your minimum distance, guys, between the two data points? It is 3, right? So 3 is the distance between which two data point? 1 and 2. So here the smallest distance is 3. Hence we'll merge points 1 and 2. We'll merge point 1 and 2. So it is merged like this, right? So 1 and 2 will be consisting of single cluster only. Blue cluster for 1 and 2, 3, 4, 5. Then we'll be actually again doing the proximity matrix because you have now, yeah, and for that 1 and 2 data point, the highest distance is taken out. So we have merged 1 and 2 data point, but the marks will be 10 only, right? So now new data will be like this: 1 and 2, 10, 3, 28, 4, 20, 5, 35. Others will remain as it is. Others will remain as it is. Yes or no? Others will remain as it is. So here we have taken maximum of the 2 marks 7, 2 to replace the marks for this cluster. Instead of maximum, we can also take minimum value of the average or the average value as well. That is not a problem. And now we'll again calculate the proximity matrix. So here we'll be having actually 4 data points only, right? 1, 2, 3, 4. 1, 2, 3, 4. Right? Now 1 and 2, then 3, then 4, then 5. 1 and 2, then 3, then 4, then 5. Right? 1 and 2, then 3, then 4, then 5. Right? We have taken the maximum of the 2 marks 7, 10 to replace the marks for this cluster. Instead of maximum, we have taken we can take this thing as well. Now this is a proximity matrix, and what is the minimum distance now? It is going to be 7. 7 is the distance that is minimum between 3 and 5, right? Between 3 and 5. So we'll merge this 3 and 5 data points again. See, we'll merge this 3 and 5. 3 and 5. 3 and 5 are merged, kept in a single cluster. So green, blue, and orange. Again, we'll find distance. Again, we'll find the data points, right? Again, we'll find the proximity matrix, right? And after finding proximity matrix, again we'll find this minimum distance. minimum distance. And now this is between 1 and 2 and 4. So we'll merge these three. So blue and green are only left with, and then we'll merge this. All clusters are, all the data points are with a single clusters, that is blue. And that is how you solve the problem. That is how the machine learning or the algorithm is will work in the backend, right? Now, how should we choose the number of clusters in hierarchical clustering? How should we choose number of clusters in hierarchical clustering? How should we do that? Yes, how should we do that, guys? So, a tree-like structure, that is dendrogram, that records a sequence of merges or splits. We are going to use that. We are going to use that. So let's get back to our teacher-student example. Whenever we merge two clusters, a dendrogram will create, and the distance between these clusters represents it in the graph form, right? So let's see how it works. We have this solution. You guys remember this thing? Now we'll just try to plot this in our graph. So first of all, we have merged 1 and 2 data frame, right? And the distance between them were 3, right? If you remember, distance between 1 and 2 is 3, the minimum distance. So we'll just take this 3 and we'll try to create a dendrogram. So we are merging 1 and 2, the distance is 3, right? Then next step, what we did is we merged 3 and 5, next step. And the distance between them was 7. 3 and 5, distance is 7, right? So again, we are going to merge 3 and 7 here. We are going to merge 3 and 7 here. And sorry, 3 and 5 with the distance 7. 3 and 5 with the distance 7 is done. Then after that, what we have done? Based on the proximity matrix, the minimum distance was for 1, 2, and 4. And what was the minimum distance? You can calculate that. That was uh, 1, 2, and 4. So 1, 2, and 4, the distance was 10, right? So we are merging that. And last, this 1 to 4 and 3, 5, we have merged it in the single data frame. The distance was 15, I think. So that's how it is done, right? That's how the dendrogram is created. Now here we can see that we have merged sample 1 and 2. The vertical line represents the distance between these two samples. And similarly, we plot all the steps that we have performed where we merged the clusters, and finally we get the dendrogram like this, right? And how we should select the ideal number of clusters now. In Kmeans, you remember we used to select we used to go with the elbow curve, right? Here, the idea is we can clearly visualize the steps of hierarchical clustering. More the distance of the vertical line in the dendrogram, more the distance, more the distance between those clusters. Now we set a threshold value first of all and draw a horizontal line. So generally we try to set threshold in such a way that it cuts the tallest vertical line. What is your tallest vertical line? What's your tallest vertical line, guys? It's here, right? This one, tallest vertical line. So it cuts that tallest vertical line. Generally, we just draw a vertical line which will cut this tallest vertical line. That was 16, 15, right? This one. And after cutting, let's say this red line, the number of clusters will be the number of vertical lines which are being intersected by the line drawn using the threshold. So in above example, red line intersect how many vertical lines? This red line intersects how many vertical line? 1 and 2, right? If we could have drawn it like this, so it is intersecting 1, 2, 3, 4. So 4 clusters. The ideal value, the best value of cluster will be 4. But since our threshold was 12, We are selecting, we are doing what we are doing is we are I mean our red line is intersecting how many vertical lines? These two vertical lines, 1 and 2, right? These two vertical lines. So the ideal value of the cluster will be it intersects two vertical lines, will have two clusters. One cluster will have sample 1 to 4. One cluster will have sample 1 to 4. Other cluster will have sample 3, 5. So two clusters will be there, ideally. And then Python implementation is something which we are going to see now. Even though we are not going to do it right now, because we still have 10 minutes left. But what we'll do is, I'll just kind of walk you through to the code of, just give me, yeah, it's only dry cough, guys. Yeah. So I just kind of walk you through the hierarchical clustering code. And anyway, we are going to do this in the tomorrow session, right? We don't have time left with us. That's the reason hierarchical clustering will do it only for same the mall customer data. We are going to do on that. But we'll actually see how to create the dendrograms and how to select the best k value threshold by uh, um, using um, hierarchical clustering, right? So importing pandas as PD, numpy as np, matplotlib.pyplot as plt, scipod.cluster.hierarchy as sch, agglomerative clustering in package. We are importing the data. Head x is something which we are selecting only these two columns, right? We already have done this project, so I assume you guys already know this thing. Then next is next is um, next is using dendrograms to find the optimal number of clusters. So we're importing scipy.cluster hierarchy as sch. What is this thing? This is just a package, guys. Hierarchy. Then plt.figure, setting a figure size, title as customer dendrograms. DND is equals to sch.endogram, shc.linkage x, comma method is equals to word, method is equals to word. And let's create a dendrogram variable. I'll explain this. What is this thing? Don't worry about this in the next session. So this is how your dendrogram is created for that particular data set, customer, mall customer, right? And then we're doing agglomerative clustering. Here, the tall value is this, right? So 1, 2, 3, 4, 5. We'll draw over here, suppose, by setting threshold as 175. So how many vertical lines are there? It is intersecting 1, 2, 3, 4, and 5. So 5 clusters should be there. So we are creating a model based on 5 cluster, and then the rest of the things are easy. Data equals to this, uh, visualizing the 5 clusters out there, and this is how your output is going to be, right? So that's what we have. And let us do hierarchical clustering. We still have 9 minutes, right? On um, on this thing, the other data that we had, right? Okay. So on for Kmeans, we are getting accuracy as like basically we'll select K cluster equals to 5 and then we'll find the accuracy. Now let us create the hierarchical clustering model. Let's build hierarchical clustering model. So mergings, just a variable, mergings is equals to linkage, rfm underscore df underscore scaled. Method is equals to complete and metric is equals to Euclidean, right? And then dendrograms is equals to mergings and then plt dot show open and close bracket. So this is going to be my complete linkage. Linkage is not defined. All right. I think the package is not imported. Yes, yes. So we'll go to the first cell itself where we have imported necessary libraries. Here, Silhouette score. After that, we need to write down import from scipy.cluster linkage dendrogram and cut tree, and then it will work. Then your hierarchical clustering will work. So what is your tallest vertical line? Let's say, let's load this. Let's wait for this. Yeah. So on this data, your tallest vertical line is, for an example, this thing. So 1, 2, 3, let's say. I'm not sure. Let's take 3. And there will not be any problem if you select wrong total number of clusters, right? As I already have told. There's no any hard and fast rule that you should select only this value, which you get from the elbow curve or which you get from other particular thing, right? What was that? Elbow curve or this part, right? Not no hard and fast rule that you should select only this one. So let's select 3 clusters and let's build a model. Cluster underscore labels is equals to cut underscore tree on mergings in underscore clusters is equals to 3 dot reshape -1 comma this. And then we'll write down cluster underscore labels. And the next part is um, you will build this model to find the accuracy. That we'll do it in the next session. All right. So in today's session, as I told, it's very basic and simple model, does not require any technical expertise. We have seen K-means, right? We have discussed K-means and we have finished the hierarchical clustering models. Now what is left is the Stillhouse score, then XGBoost. So basically boosting is remaining and KNN is remaining. That we can perfectly finish it within one session. And after that, we are going to start with the very interesting topic, that is deep learning, right? So we are going with the good pace now. Deep learning will be your last module. And in that, you can see whatever is there in your syllabus, we'll be starting with that, right? Yes. Now, do you have any questions, guys? Whatever we have discussed till now, do you have any questions in this? Yes, guys. All right, then we'll stop here for the day. Just revise this thing. Do go through this hands-on part, and then if you have any questions, we'll discuss that in the next session. Right? Chalo. All right then. Thank you. Happy learning. Bye.